today the floor function again. That will be awesome. Okay guys, so today another integral from the MIT Integration Bee, this time an integral that appeared in 2015, I think. So we're supposed to evaluate the integral from 0 to a1 of 1 divided by the floor of 1 minus the log base 2 of x dx. I love it. Okay, so, well, how are we supposed to solve it? First of all, we should kind of notice that this log base 2 of x has kind of like a discontinuity on as x approaches 0. I mean, as x is a 0, log base 2 is not continuous, so we should rewrite this entire integral in terms of a limit. So we should rewrite it as, let's say, a limit as some kind of a t approaches 0 from above of the integral from t up to 1, once again, of dx divided by the floor of 1 minus log base 2 of x. Perfect. Well, now, what can we do here in order to, well, get anything valuable out of it? I mean, if you watched my 2 previous episodes of Laidback Math, when I also integrated some stuff with the floor function, you probably already guessed that what I want to do here is change those intervals, change those endpoints of those intervals I'm integrating over, such that I will be able to say that my entire floor right over here is an integer of some sort that I'm able to just, you know, get out of the integral, because it's just gonna be constant with respect to the variable that I'm integrating with respect to, which is x. Okay, so what kind of thing would make, let's say, this log base 2 right over here an integer? Well, if x was equal to 2 to some kind of a power, that would be, let's say, an integer, well then absolutely and definitely we would get that this thing right over here would be an integer. Okay, well, we can actually do something about it. I mean, we could rewrite this entire integral, this entire limit, as, let's say, a limit as some capital N approaches infinity of an integral, oh, that's an awful looking integral, of an integral, let's say from 1 over 2 to the power of the capital N up to 1. Once again, of dx divided by the floor of 1 minus log base 2 of x. Perfect. Well, now we see that on one of those endpoints, definitely this log base 2 of x will be equal to negative capital N. The only problem is that we can't really just say that it's gonna be equal to this thing, you know, in the entire interval. So we have to split this entire limit, this entire integral, into a couple of more integrals. I'd actually like to make it equal to, or maybe actually I will write it somewhere here, to something like, you know, limit as the capital N approaches infinity of, let's say, an integral from 1 over 2 to the power of this capital N, then up to 1 over 2 to the power of this capital N minus 1, then plus the integral from 1 over 2 to the power of the capital N minus 1 up to 1 over 2 to the power of the capital N minus 2, and so on and so forth. I would be just summing up those lovely integrals until I would get to, let's say, 1/4 up to a half, and then plus the integral from a half up to 1. So we could, I mean, we see that all those integrals together, they sum up to, well, all those intervals from all those integrals, they sum up to the interval from 1 over 2 to the power of the capital N up to 1, which is, well, the exact interval we are integrating over in the original problem statement. So, well, that's pretty lovely. Let's go and do it. If I were to write this entire thing in a little bit, let's say, more convenient way, what kind of an expression I would have to use? Well, probably the sigma notation, because it's just a discrete sum. This is just a discrete sum of a couple of differently whatever, of just some integrals. Yeah, so that would be the limit as the capital N approaches infinity of the sum of, from, let's say, lowercase n equal to of 0 up to the capital N minus 1 of the integral. I want this integral to look nicely, or I just can't do it, from 1 over 2 to the power of n plus 1 up to 1 over 2 to the power of n. Yeah, so we said I had to put this this capital N minus 1 here in the sigma upscript. That's because I have 1 over 2 to the power of n plus 1 here as the starting point of the first interval I'm integrating over, and that's gonna be the integral of dx over 1 minus logarithm base 2 of x. Perfect. Okay, but now, can we do anything with it? Well, absolutely we can. The entire point of changing those intervals was to, well, get something interesting here in this floor. And so let's try and see whether we actually got anything interesting. Well, we know right now that whenever x is in between 1 over 2 to the power of n plus 1, yeah, so x is greater than 1 over 2 to the power of n plus 1, then, and it's less than 1 over 2 to the power of n, yeah, then the log base 2 of x is gonna be between negative n plus 1, the log of x, log base 2 of x is going to be between negative n plus 1 and negative n. So now if we just go on and flip all those inequalities, multiplying everything by negative 1, we would get that n plus 1 is greater than negative log base 2 of x, which is greater than n. And we could just go on and add 1 to everything in this entire inequality, getting n plus 2 is greater than 1 minus log base 2 of x, which is always greater than n plus 1. But, well, that's pretty awesome, because now I can just take floor of this 1 minus log base 2 of x, and I see that this will actually always be equal to n plus 1 over the entire interval between 1 over 2 to the power of n and 1 over 2 to the power of n plus 1. So you can just go on and take this thing. Yeah, we can just go on and take the fact that the floor of 1 minus log base 2 of x is going to be equal to n plus 1, and write our integral right over here in terms of our founding. Yeah, so it is going to be equal to a limit as the capital N approaches infinity of the sum as n, a lowercase n, goes from 0 up to capital N minus 1 of, well, just an integral of 1 over 2 to the power of n plus 1 to 1 over 2 to the power of n, and then, well, just 1 over n plus 1 dx. But we see that this 1 over n plus 1 is just a constant with respect to x, so we can just go on and take it out of the integral altogether. And so what we will get after doing that is just pretty nicely, oh my god, I don't really want to write this thing down, and again I will just, oh yeah, that's a nice thing. That's a nice thing to do. I like copying stuff. Okay, now it's better. After this small cheating, I only have to go on and move this integral and, you know, take this 1 over n plus 1 out of it and write this dx right over here. But, well, we know that this integral right over here is just gonna be equal to 1 over 2 to the power of n minus 1 over 2 to the power of n plus 1, but that's just equal to 1 over 2 to the power of n plus 1, and so we can once again rewrite this entire thing as, yeah, nice, as just the limit as the capital N approaches infinity of the sum as n goes from 0 to the capital N plus 1 of 1 over n plus 1 multiplied by 1 half to the power of n plus 1. But, well, we see that this thing right here is just a geometric sum, which is actually pretty nicely convergent. Yeah, I mean, you could actually even see that this entire thing is absolutely convergent. I mean, if you were to take the absolute value of, oh my god, the absolute value of a half to the power of n plus 1 all over n plus 1 and divide it by the absolute value of 1 half to the power of n all over n, sorry, not n plus 1 but just n, well, this thing would be less than 1. So this entire series is, well, absolutely convergent. That's absolutely awesome. Well, why is it awesome? You see, just kind of think about how could we be smart about rewriting this 1 over n plus 1 multiplied by 1 or 1 over 2 to the power of n plus 1. Well, we have some number here that is risen to the power of n plus 1 and we are dividing it by the same number we raise it to the power of. This looks like an integral between 0 and something, and that something is a half. So actually this entire thing looks pretty similarly to, let's say, the limit from as capital N approaches infinity of the sum as n goes from 0 to capital N minus 1 of the integral from 0 to a half of x to the power of n dx. And one more thing is that, well, as this sum is convergent, as I've proven right here by the, I think it's D'Alembert criterion, but I'm not quite sure honestly, I can actually go on and, well, get rid of this limit right over here and just say that I'm summing from 0 to infinity. That's absolutely perfect, because now what I have here is just an infinite sum of some integrals. But I can use the dominated convergence theorem because I know that this thing is absolutely convergent. This sequence right over here is absolutely convergent. So I can just go on and use the dominated convergence theorem, which I will definitely make a video about one day on this channel, and just go on and change the order of summation here. So what I would like to do is take the integral from 0 to a half of the sum that goes from 0 to infinity of x to the power of n dx. But the nice thing is that, once again, I know that this sum here is convergent because x is between 0 and a half on this interval. And so I can just say that this is going to be equal to the integral from 0 to a half of 1 over 1 minus x dx, because this is exactly what this sum will converge to. But, well, this integral is not very hard to evaluate. Just plug in u equal to 1 minus x, you will have negative du equal to dx, and what you will be left with is just negative natural log of 1 minus x in the bounds of 1 and a half to evaluate, which will be equal to negative natural log of a half and minus that natural log of, well, 1 minus 0 is a 1, so that's just going to be a 0. Now we can just go on and suck this negative sign here into the natural log, getting that is going to be equal to the natural log of 2, and this is exactly what we were supposed to find. This is our beautiful solution. Okay guys, so, well, once again, what did we actually do here in this problem? Well, we're supposed to evaluate the integral between 0 and 1 of the x divided by the floor of 1 minus log base 2 of x. So what we did is, first of all, we noticed that log base 2 of x has a discontinuity at x being equal to 0. So we just rewrite this entire thing in terms of a limit as t approaches 0 from above of the integral from t up to 1 of dx by the floor of all that crap, which then we just thought to ourselves, how can we, let's say, play around with those intervals such that this log base 2 of x will be, you know, some kind of an integer I mean that we will have a bound only that is an integer, so that we will know what the floor of this entire expression right over here actually is, so that we can then go on and just take it out of the integral as it becomes a constant with respect to the integrated variable. And then what we saw after doing all of that nice stuff with that floor function was that we ended up with a absolutely convergent sequence, which was lovely because this absolutely convergent sequence was also rewritable. It was possible to write that sequence in terms of another integral, but well, since it was absolutely convergent, we had no problem with using the dominated convergence theorem and just changing the order of summation. So first of all, we took the infinite sum of all of that x to the power of n's, of the small n's, for x's that are between 0 and 1, which is absolutely convergent, and then just integrated the result with respect to x, calculated the result in the bounds of integration, and got that our beautiful answer is the natural log of 2. Hope you guys enjoyed it, and see you in the next one. Bye.